So we have here a traveling wave, and there is no end to it. So this is like a particle just traveling and not encountering a boundary. It's just going to continue. But so this is what chapter 16 is, and it is described by the formula of the displacement for a wave, right? D is the amplitude, so it'd be 0.25 centimeters times sine of 2 pi over the wavelength, which I think the wavelength here is about 4 centimeters. Or it should be, let me just write it down, what this wave actually is. Let's just write the formula for this, okay? Because the amplitude is 0.25. So this wave is D equals 0.25 centimeters, right, in these units, times sine of, if you remember last time we measured the wavelength of this thing and found that it was 4 centimeters. So it's 2 pi over 4 centimeters times x minus 2 pi over the period, which is the same as 2 pi times the frequency. The period, if the frequency is 1.5 hertz, then the period is like, we measured this as well. The period is like 0.67 seconds. And so writing it like that, it would be 2 pi over 0.67 seconds times time. That's the formula for this traveling wave. If you change the frequency, then the 2 pi over t will change, but that will also make the 2 pi over lambda change, because remember the wavelength and the period are related by the speed of the wave. So one changing causes the other to change. And this is just for a single wave. Now what we want to do is start adding waves together. And so what I'm going to switch to the pulse so we can see how a couple examples of how they add together. And then we'll move on to the standing wave part. Clear that. So let's do the pulse. And I want to do the fixed end. The fixed end is the one I want to start off with. Okay, so again, I'd actually increase this to 0.75 again, just so you can see what happens. So again, sending in the pulse. Oh, that's right, we have to go over here. Right here. So again, that's what we see. It reflects under itself when it's at a fixed end. If it was the loose end, remember, it would bounce back without going under itself. So what's going to happen if we send in a second wave? They look at those two spots, they look like they kind of bounce off each other. And it's worth pausing and kind of following through step by step. Okay. The principle of superposition, so if these waves are heading towards one another, the principle of superposition says the actual amplitude of the wave actually depends on the sum of the amplitudes of the waves at that spot. So we have two different pulses heading at, say, this, the location right in the middle. And so when we have that, then if we add the things when we add the things together, you're going to see a location where eventually the top pulse and the bottom pulse. So as the top pulse is moving to the right, the bottom pulse is moving to the left. So there's going to be a moment when they actually cancel out moving forward. So at this point, you have the top pulse, which is moving to the right, is literally at the very same position as the bottom pulse is, but it's moving to the left. And so as they separate, then you start to see the pulse on the top pulse moving to the right, you start to see the bottom pulse moving to the left, and then they separate as they're moving past one another, and then they continue along and then do what they do. So, and then of course that would happen right here as well, where they didn't bounce off each other, they pass straight through each other. Okay, and so what I'll do now is pause or play that again, but I want to get to a loose end. What happens when I change the fixed end to the loose end? It looks like it's adding, I'm going to I'll restart it. So I'll get rid of this damping, cut out all the energy, and I'll send a couple more. Oh, geez. Interesting. Let me just reset it. So I think by resetting it, I have to change. Yeah, I have to change back to pulse, and I have to go back to loosened, undamp the thing. It's fine. Hopefully it'll be worth it when we see these two waves together. Okay, so now we have it set up again for 2 pulses. So again, this is the pulse of the loose end. I'm going to send another pulse, and boom, they add together. So when they add together, again, it kind of looks like they're bouncing back, but they're not. They're just traveling straight through one another. And so if we pause that now, this one, when we're adding them together, it's a bit more what you would expect, I think. I'm going to wait. Okay, so this one is bouncing, this one is reflecting as this one is moving towards. And so as it, so it is bouncing off the edge, but once it moves in here, now you see they're getting closer together. And then this is the time, instant in time where they're at the same spot, and you see a double triangle. And so the wave, so there's the two waves, the 2 triangles are stacked on top of each other. And so you see a double triangle of twice the amplitude when they add together. So the amplitude doubles, and then of course they separate again, and then, you know, continue doing what they were doing. And then I guess on the bottom, they're doing what we just saw, because it's at the fixed end. And so one of them switched a phase factor of pi over 2, right? And then they just continue. So that's the basics of superposition. When 2 waves come together, the resulting observation is always the sum of the amplitudes at each point. So that's just for the 2 pulses. If we want to continue, extend it to include traveling waves and not just a pulse, then I guess that'd be the easiest way to do it, wouldn't it? Let's go back to the fixed end. Okay, and now I'm going to oscillate it. So once again, I'm going to change these things. I'm going to lower the damping. In general, if you start the thing at any frequency, you're going to get some strange shape. But there's a special frequency, and this is where this concept of standing waves comes in. Okay, the special frequency that I want to put this string at is 0.4 hertz. Sorry, oh shoot, I should have changed it to oscillation. The pulse width I'm not interested in. It's oscillation. So it's oscillating, and you're starting to see that's kind of adding together, but it's also kind of wobbling out, and you're not seeing, it looks like it's trying to be a standing wave, but it's just not. And that's because we're not at the right frequency. So if I change this frequency to 0.4 hertz, and I'm going to damp it so I can cut out all of this extra noise to where it's very nearly 0. Then I can remove the damping, and I can show you what pattern is formed. So we see this kind of jump rope pattern, right? This is like when you're playing jump rope as a kid. I'm going to lower the amplitude so don't add any more energy. But this is a standing wave, okay? And it looks pretty good because, well, it's the first one. But what you see is there's a one wave from this source. There's one wave traveling from the right, or from the left traveling to the right. But when you have the fixed end, there's a second wave traveling to the left. And so they add together and they form this shape. So this is called the fundamental harmonic of it's called the fundamental harmonic of this string with a fixed tension. So I'm going to damp it once again, and damping it really just cuts out most of that energy. Next frequency, I think we started this again last time, was to go to 0.8, but I want to be more systematic about it now. If we go to 0.8, then again, what do we see? We see this second harmonic. And a couple things to note about this harmonic. So these oscillation parts, they're oscillating at twice the frequency as the first one. So they have more energy than the first one does. And again, if you go to 1.2, you do the third one and so on. If you have, and of course, this isn't a perfect simulation, so it's going to kind of numerically sort of trail off, but then it'll start up again. So it's kind of close to this resonance thing. If you, again, keep adding, if you go to the next multiple of 0.4, you'll get 1.2 hertz, and so you get the 3. And again, you see that dot in the middle, it's very nearly at rest. It's very, very close to being at rest. The two ends of the rope are nodes, and this middle part are nodes, and the two maxima and minima that are wobbling, those are called antinodes. And so what happens if you try to do this on a loose end? If you try to do it with one end being loose, then the pattern messes up and you don't produce the pattern, right? This is not a standing wave. It's just kind of jumbling all over the place, isn't it? So the question remains, is there a way to produce a similar pattern on where one end is fixed and one end is loose? And the answer is, well, sure. Of course, what we have to do is, let's just damp it. Easiest way I can think of to do it. Let's change the frequency though. It turns out that with one loose end, then the first frequency where you get this effect isn't 0.4, but it's actually 0.2. So going down to 0.2 and then undamping the thing, we see that we form the first mode of oscillation for a pattern or a medium with one end being the node and the other one being an antinode. Okay, so this, and if you notice, this is like 1/4 of a wavelength, right? So the first pattern that you make when you have a node and an antinode is that of a half of a sine sort of envelope, half of it. So that is the first harmonic. And you might think, okay, so this was 0.2 hertz. So you might think, well, okay, what's going to happen? Maybe if I go to 0.4 hertz, I would double it and I would get the full pattern. When in fact, if you look at it, I'm going to damp it as usual. Got to heavily damp the system to get it back to suck away all the useful energy. Going back to, so if I go to 0.4 hertz, oops, sorry, 0.4, and then I undamp it again, what do we see? Do we see the next pattern? Not really. Okay, we don't really see anything forming. Okay, we don't see any standing wave pattern. Even if you even if you ramped up the amplitude, you're not seeing anything that's like a standing wave. It looks like there's something that's trying to, but it turns out that 0.4 is not the spot for it. It's actually, got to tune all these things. It's actually 0.6. So it's not 0.4, but it's actually 0.4 plus the original one, which was 0.2. So if you do 0.6, what do we observe? Well, it looks like we still don't observe much. Let's go back to, let me change the amplitude a little bit. Certainly does take a little bit of time to get this right. If I do a lot of damping and then I start over. We do see the second pattern emerging. And this one's really nice. So this is the second pattern that's formed when you have a node on one side and an antinode on the right side. So what's the difference between this pattern and the one that we first saw? You have one complete sort of sine bump and then one half of a sine bump. And that's very characteristic of these wave patterns where one is where one is a node and one is an antinode. And I'll talk about what types of antinodes there are later. But yeah, that's the first pattern. So the similarity between the standing waves that are formed with two nodes and the standing waves that are formed with the node-antinode combination is that each successive pattern is that same multiple, that same 0.4 hertz later. Oh, I didn't mean to pause it, but it's just switched. So what would happen if I go to 1 hertz then? If I go to 1 hertz, again, damp it and then start over. What do I observe? Now you observe what you would expect for the next mode. Now you have one complete new bump and the original full bump and still a half bump on the side. So, and it's hard to tell, but especially because here it's starting to kind of phase out. But at this point, even though it's oscillating, it's still a node because its amplitude is much less than these 3 antinodes. Okay, so we actually have 3 antinodes right here. And that's about as good as it gets for this simulation. Okay, so when you have a node-antinode pair, the harmonic each of the harmonics still increase by that first frequency, the 0.4, but it's just all of them are shifted by 0.2 actually, which makes it really interesting. Okay. You can also consider, although the simulation doesn't really allow it, and I've never even seen a good simulation of this, you can also simulate an antinode-antinode pair where both ends, let's say if you were able to get somehow both ends of the string to be antinodes, then the first pattern you would see would be something like this. The top end or the left end would be on the bottom while the right end would be at the top. And so it would be 2 half bumps, but it would be 2 half bumps. So there'd be 1 node and 2 antinodes to start. That would be the first pattern. And so hopefully you can imagine that. The second pattern, interestingly enough, is like something like this. And then there's 2 nodes right here. And so it oscillates to something like this. So this is when you have 2 nodes, or this is when you have 2 antinodes on the ends. This is the pattern that forms. And again, I don't have a simulation for it, but you can imagine that when you have 2 antinodes, you always have a half bump on either side, and then every successive harmonic creates a new complete bump in the middle. So the third one would be what? That would be the odd one. So it'd be like that. Something like that. The drawings are getting worse, but yeah, something like that. So each successive harmonic adds a complete bump, and there's always still the half bumps on the 2 sides. One of the ways in which this can actually be produced, well, besides sound, would be if you had a water tank. If you had a water tank and you kind of push the water on one side down, then the water isn't fixed. The water in a tank isn't fixed to be at a specific spot. It can, wobble up and down. And so that would be how you create that pattern. Again, not that hard to imagine. I've never seen a good simulation or even demo of it. So that's a summary of these standing waves. And certainly it applies not only to strings, but also sound waves, light waves, anything that has a wave behavior to it has these standing waves. So that's the conclusion of this simulation. Next, we're going to talk about the mathematics of it.